Okay, so if we're talking about ring contractions, so let's draw a couple of six-membered rings. So when you see this, you should immediately become aware of the tert-butyl group up here, and know that because there's a tert-butyl group, that always wants to be equatorial. It never will be axial because there's too much steric hindrance, steric interactions between the 1,3 diaxial interactions. So this tert-butyl group always will have to be equatorial. The other thing, of course, you should do is number your carbons. 6. Good. Get your carbons numbered, and then I would just start drawing a chair conformation. So you draw a chair. I'm going to number, let's see, 1, 2, 3, 4, 5, 6. So the way I know how to set this is that I know the tert-butyl again has to be equatorial. So the tert-butyl is on carbon 1, and it's equatorial, so that means it's up, equatorial. All right. On carbon 3, the nitrogen is on the same side as the tert-butyl, so it's also up. And so in this case, it's also going to be, wait, did I do this wrong? I want to draw this different. Let me change this. Nope, they're going to let me. All right, sorry. So the N2 and the tert-butyl are on the same side. So the N2 is going to be going up, and the OH is going to be going down. Right? So everything's equatorial in this case. Right? So the point of this is, right, to think about, right, what we're thinking about here is, right, elimination reactions, right? We're thinking about molecular orbitals, where they're at, right? So the question is going to be, is this, like, we're going to, essentially, we know we have a good leaving group. That should be the N2. That's pretty obvious. The question is, are we going to go through a carbocation or not, right? And the other question to think about is, where is sigma star for this carbon-nitrogen bond? Where is sigma star? Well, sigma star is right here. That's where sigma star is at. Now, what is perfectly lined up with sigma star here? This is where it gets a little weird. Which bond is lined up with sigma star? The bond between which two things? 1 and 2. Not 1 and 2. 3, 4, and 5. This bond right here is lined up. Right? The bond between 5 and 4 is lined up. Now, 1 and 2 probably is lined up too, but if you move this bond, you'd leave a carbocation on carbon 4. Now, why is that okay? Because how many ways to stabilize a carbocation? Hyperconjugation, pi bond resonance, or lone pair resonance, right? If I put a plus charge on carbon 4, that's good because this oxygen has lone pairs. It can help stabilize it with resonance. Right? So this bond, these two electrons are going to go there. And that's where we get our first ring contraction. Right, as that bond breaks, right, the N2 obviously, I got to draw that leaving. Right, we lost N2 gas. Someone should ask, you didn't balance your charge, right? But did I? Of course I did. What's the N2 resonance structure look like? Remember, N2 is that, right? So I did balance my charge. The nitrogen, the first nitrogen that's bonded to the carbon 3 has a plus charge on it. That's why it's such a good leaving group. Right? N2 has a plus charge on it. So really they all show little plus charges. Should be a plus charge here to start with. Sometimes they don't draw that in though as a plus charge. They just draw it in as N2. I will. 1, 2, 3, 4, 5, 6, right? 5 and 3 have the new bond. 5 and 3 have the new bond. And 4 is one with the carbocation. And the reason 4 will have a carbocation again is because the oxygen has lone pairs and it'll stabilize it with resonance.
So could it do it the other way if oxygen was on 5?
So it will show another possibility too here. What else could happen? In a different conformation.
Is there any significance to the OH kind of going from equatorial down to equatorial up or not?
No, because now, right at this point, now it's free rotating, so it doesn't really matter. Yep. So then, what can happen here, right? If we draw the resonance structure in, electrons go down. We'll end up getting here. Essentially end up getting an aldehyde after we regenerate acid, right? So that'll leave. And here we get a 5-member ring now. And notice on the aldehyde, it's on the same side as the tertbutyl. If we went down number of carbons, 1, 2, 3, 4, 5, 6. What? And then you lost a hydrogen. And plus H plus. Carbon 4 always had that hydrogen. This carbon always had this hydrogen. It was just there, I didn't draw it in. Right, carbon 4 has one hydrogen here. That never changes. So that's one possibility from this conformation. There's another possibility too. So we could draw this way. So let's redraw that same 6-member ring again. Oops. Okay. Number of the carbons the same. 1, 2, 3, 4, 5, 6. So this was kind of more like I don't want to call this one up here. It's certainly not it's not like an E1, really. But it's not necessarily, it's a migration, right? It's a ring contraction. But we also could do it so, right? Notice what we can't do, right? We can't form a pi bond here, right? Because, right, sigma star is still over here, right? We have to kick out N2, we have to attack pi star. Or N2 could just leave, right? It could just take off. So that's the other thing that could happen, is that N2 could just straight leave. So if N2 leaves, what are you left with? Now you have a carbocation. One, 2, 3, 4, 5, 6. So now you have a carbocation. And what you can do now, essentially, is, right, now you have an H there that's on carbon 4. Right, again, why do we want to put the carbocation where? Carbon 4. Right, at the end of the day, we want to get the carbocation on 4 because 4 can stabilize the plus charge because it's next to the oxygen with the lone pairs. So it's going to do a hydride shift.
matter if it was axial or equatorial?
Now it does, the axial one lines up kind of better. But the big take home message is if you're going to put a carbocation, if you're going to migrate and move stuff around, you might as well move it so the carbocations next to the lone pairs. You want the carbocation next to lone pairs. That's the big take home message. And again, what's going to happen? Electrons go down. Let's too tight in that corner. So now you didn't make an aldehyde, right? You made a ketone. Once these electrons go back, right, you get a ketone. Right, so this conformation here, where there's a tert butyl and it's has two trans, right? The N2 and the OH are trans to each other on adjacent carbons. There's two possible products. You can get an aldehyde, right? You can get an aldehyde product, or you could get a ketone product. A 5-member ring aldehyde or a 6-member ring ketone. It's two possible products there. So this is just another possibility. So last time we did it, we had a 6-member ring, and the N2 and the OH were trans to each other, and that led to two possible products. But what if we had a different starting conformation? So again, we're going to be anchored by a tert butyl, and we're going to have the N2 and the OH this time be cis to each other. Be cis to each other. So what's that going to look like in a 6-membered ring? One, two, three, 5, 6, 4, 5, 6. All right. Okay, so let's see. Tert butyl's up. That means N2 needs to be down, right? So that's going to be axial in this case. The OH also needs to be down, so that's going to be on carbon 4. So that can be axial or equatorial. On carbon 4? Equatorial. Good. Now in this case, right, where's sigma star for this N carbon bond? Straight up, which is exactly in line with, right, the CH on carbon 4 as well. Right? It's all lined up. That looks almost like, right, so essentially instead of doing elimination here though, we're still going to do a hydride shift. This hydrogen is going to shift over, attack that, while the N2 leaves. So it really is stabilizing to form a carbocation here. Right? Carbon 4 wants to have a carbocation. That lone pair resonance is really stabilizing. So what do you end up with? Not a ring contraction. Anything cool like that. You end up with H's on here. A plus charge here with an OH. We number our carbons. 1, 2, 3, 4, 5, 6. Electrons come down to draw that resonance structure with a full octet. 5, 6. Alright, the H can just fall off, and we'll get the final product. Now you'll notice this final product is just like one of the products we had before, right? But this would be the only product we form with this conformation, this stereoisomer, right? You'll notice I think this one was a diastereomer to the last one, right? The stereoisomer for the nitrogen was different on this one than the last one. So this diastereomer only gives one product, whereas the other diastereomer gives two. All right, so if we're talking about a question about the anomeric effect. Essentially what the anomeric effect is especially in sugars, it's the tendency for substituents in a six-membered ring with the heteroatom. So a six-membered ring with a heteroatom. Normally we'd say most things never want to be axial. But in the position right next to the heteroatom, right, it's called the anomeric position, naturally enough. Things in that position want to be axial. Now, why that is the question, right? There's a couple theories here we can postulate, but nonetheless they do, right? And a big reason it works that they do because that's how our phosphate linkage backbones are in our DNA, so that's kind of important, right? There's also explaining some of their activity as well, right? How they react, the anomeric effect does too, we can look at. So let's look at an example of a sugar. Oops. So here's a basic sugar molecule. Number of carbons are in oxygen 2, 3, 4, 5, 6. Let's put this into a six-membered ring. Let's make it nice and big. I'll put my oxygen here. Let's see. 1, 2, 3, 5, 6. So 2, I'm going to make 2 axial up. 3 is going to be equatorial up, that OH. 4 is going to have to be equatorial down, that other OH. 5, equatorial up. 6, equatorial down. Right, so you can see most things, everything else wants to be equatorial, is equatorial, except for the OH on carbon 2. Now, why would I want to do that? Okay, well, let's start thinking about what are some possibilities here.
So it doesn't line up.
Well, steric arguments, right? And if you think about sterics, right, there's CHs here, right? That in theory, that OH is going to bump into, right? Those diaxial interactions. This is axial, this is axial, this is axial, right? They're going to bump into each other. Why not just have that OH be equatorial? Well, one of the reasons possibly why people like to show, you can also think about the lone pairs on the oxygen nitrogen has 2 lone pairs. The lone pairs take either an axial or equatorial position as well. Right, so one lone pair, right, is sticking out equatorial, and then another lone pair is sticking out axial. Now the axial one lines up pretty well with sigma star from that carbon-oxygen C2 bond, right? And that can help stabilize the molecule, right? It's kind of a way to spread electron density out. Right, because you can think of a carbon-oxygen bond as a pretty polar bond, right? So it's not fully breaking the bond, but it's also helping spread out some of the electron density. So that helps stabilize the molecule, right? So the question is, what's worse or what's better, right? How bad is this diaxial interaction versus how stabilizing is this interaction? So this must be stabilizing enough that the cost of having it axial is worth it. And it doesn't take a rocket scientist to take this for another step, right? What we just did, right? If these electrons can fully go in here, this can leave, right? And we formed an oxocarbenium ion, which is a good place for nucleophiles to attack. Yeah, so there's a question, Why didn't it go this way? Because carbon 6 is bonded to another carbon. That's not a polar bond. Carbon 2 is directly bonded to an oxygen, so that's why. Right, so right, it's always going to be this anomeric site is the one adjacent to the oxygen, and it has to be directly bonded to another oxygen. And we never would draw it with the ring flip, right? Because in the ring flip, yes, this would be equatorial, but then all of these would be axial. And then we'd lost the anomeric effect here. So it certainly, this is the best confirmation. But the question is, why have this axial? Why does it not have this equatorial like all the others? It's because there's this possible, no, there is a savings of energy here to have it axial. This is from the Danheiser Jack's paper. Scheme 1, and it's showing pathway B.
They both do it, so I just put it
Huh? Pathway B. So this is the cyanoene. I'm going to simplify this a little bit. Triple bond. H. I guess I'm not going to simplify it. Well, yeah, I am. I'm going to make this an R. This is going up, out, down, down, C, N. Let's number these things. 1, 2, 3, 4, 5, 6, 7, 8. I'm not gonna call the H9. All right. And that's going to form just make sure I number my carbons right. 8, 7, 6, 5, 4, 3, shoot. Oh, 2, 1. Right, so we got a logical numbering system. Now we need to say which bonds are broken, which bonds are formed. Right? So bonds broken. Which bonds do we break?
Pi bond between 6 and 7.
Pi bond between C6 and C7. Yep. Sigma bond between 2 and N? It's a pi bond. Yep. So I'm going to say pi bond between C2 and N. Sigma between C8 and H. I think that's all the ones we're breaking. Bonds formed. What bonds we form?
Between 7 and 8.
Pi bond between C7, C8, good.
Sigma bond between 2 and 6.
Sigma bond between C6 and C2, good.
Sigma bond between, I don't know what H that is.
N and H, right? And 1 and H. I think the H, right, has to be, the NH bond has to be the H that's from C8, right? Alright, so this is an electrocyclic ene reaction. Right? This is an electrocyclic reaction. Alright, what was the definition of electrocyclic reaction? Incidentally enough, what do we have for definition? Okay, so let's move some electrons. I'm going to have the pi bond between the carbon and nitrogen attack that H. I'm going to have these electrons, CH and 8, go there between carbon 8 and carbon 7 to form a pi bond. And then the pi bond between 6 and 7, I'm going to have attack carbon 2, which just lost that pi bond. That gets us to the formed product. So we make a allene, right? This is called an allene. That's what we made there. Number of carbons, bonds broken, bonds formed.